This video continues our idea of tension, and this time we're talking about tension in things that are being pulled by a rope or a string. And the question is, what is the tension in the rope used to pull this box at a constant speed of 1 meters per second if there's a frictional force of 5 newtons? So what we hopefully remember is our idea of equilibrium, which means the sum of the forces acting on this have to equal 0. And there's two situations where that occurs. It's when something is at rest, or it's when something is moving at a constant speed or velocity. Number 2 here is our situation. We have something moving at a constant velocity, and when we think about the forces that are acting on this, there are basically 3 of them, or 4 of them, sorry. We have the weight of the object pulling it down. We have the normal force, N, pulling that up. Now the weight is again going to be mg. In this case, it's going to be 10 times 9.8 meters per second squared, or 98 newtons, and that will equal the normal force of 98 because this object is just simply sliding across the horizontal surface and not moving. Now we said there's a frictional force of 5 newtons, and these vectors are not drawn to scale, but we have 5 newtons pulling this backwards. So this is moving at a constant speed, and that means the sum of the forces are equal to 0. So in this case, it'll be the sum of the forces, and in our x direction, they're equal to 0. And we know there has to be some force pulling this forward. We'll just call that F, and a force going back, which is 5 newtons. So I'm sorry, we don't want to call that F. We want to call that the tension. That was my mistake. There's a force pulling on this chain or rope, but that's putting tension in there. So put the tension in for T. We need to define a positive and negative direction. We're just going to say, in this case, things that go up and to the right are positive. So in this case, the tension, T, is positive, minus 5 newtons, which is our frictional force that equals 0. So in something that's moving at a constant speed, the tension that has to be put into this rope to pull it is just equal to the frictional force, and that'll keep it moving at a constant speed. Changes slightly when you have something that is accelerating. So we went from a situation that is moving at a constant speed to one that's now going to start to increase velocity. So now our sum of the forces equals 0 argument is not going to hold. Here is, what is the tension in the rope used to pull the box if it is accelerating at a rate of 1.5 meters per second squared if the frictional force between the surfaces is 12 newtons. So, again, we can add our 2 different forces in the y direction if you want to. The weight of this, which again is 98 newtons pulling down, and the normal force N also equal to 98 newtons pulling that upward. We know there are frictional forces pulling this backwards again at 12 newtons. And for our purposes, let's say up is positive and so is going to the right. And the last force we have now is a tension that's pulling that forward. And we're going to call that tension T again. So here are 4 forces that are affecting this. This time we have to know that the tension has to be more than what it was before, because in order for this to move faster, it's going to have to be able to overcome friction. So again, we're going to make an F net equation this time. F net is equal to the net forces acting on it, and this time this is just simply equal to the formula mass times acceleration. That's basically just restating Newton's second law. So the acceleration is moving to the right, and it's basically this mass times acceleration formula. This is our overall when you combine all the forces. So we have to, it's almost like we're doing a sum of the forces, but this time it doesn't equal 0 like it was before. So we said positive is going to the right, so it's going to equal the tension minus the frictional force. Now we know what the mass of this is. This is 10 kilograms. We know the acceleration we want is 1.5 meters per second squared. That's going to equal the tension minus the 12 newtons of friction. And then we can multiply this out. We're going to get 15 newtons is equal to T minus 12 newtons. Got to be careful. Sometimes people, what they do is they didn't subtract these two and they think that it's 3 newtons, but actually you have to add 12 to each side. And when you do that, you end up with 5 plus 2 is 7. 1 plus 1 is 2. 27 newtons is equal to T. So that tells you that the total tension in this string is 27 newtons. And again, that hopefully makes sense because you have to have at least 12 newtons of force to overcome friction and to make this accelerate. And this is a decent size. It's still probably in the 20-some pounds area, more than 20 pounds, obviously, because there's 2.2 pounds per kilogram. It'd be 22 pounds. It's going to take a lot of force to make this move. So 27 newtons is definitely a reasonable answer. So that concludes tension part 2 when we're making something accelerate in a horizontal plane.